May 30, 1942, London. Beneath the fortified corridors of the British War Office in Whitehall, a closed-door meeting brought together some of the most experienced naval officers, engineers, and strategic planners in the Allied command. At the center of the room stood Vice Admiral Louis Mountbatten. When he spoke, the proposal he laid out seemed to defy not only military convention, but basic logic. If suitable ports cannot be seized, he argued calmly, then we may be forced to build our own elsewhere and bring them with us. The reaction was immediate. Senior officers laughed openly. Sarcastic remarks echoed across the table. For men trained for decades in naval logistics and coastal warfare, the suggestion sounded absurd. Harbors were not mobile objects, they were massive, immovable systems tied to geography, geology, and infrastructure. The English Channel alone, notorious for violent tides, unpredictable storms, and heavy enemy surveillance, made such an idea appear impossible. The concept required believing that an entire port could be manufactured in sections, transported across hostile waters, and assembled on an enemy coastline while under fire. To most in the room, it bordered on fantasy. Yet buried within that moment of mockery was the origin of one of the most radical engineering endeavors of the Second World War. What was dismissed as madness would soon evolve into a solution that redefined amphibious warfare. It would force German planners to confront a threat they had never imagined and dismantle their core assumption that without ports, an invasion of Europe could not survive. The outcome of D-Day, historians would later argue, depended not only on infantry tactics or air superiority, but on mathematics, material science, fluid dynamics, and the bold notion that logistical impossibilities could be engineered away. Steel, reinforced concrete, hydraulic balance, and tidal timing would prove as decisive as rifles and artillery. That realization, however, was written in blood months earlier. August 19, 1942, Dieppe, France. The lesson arrived violently on the pebble beaches of Dieppe during Operation Jubilee. More than 6,000 Allied troops, the majority of them Canadian, were sent ashore in what was intended as a limited assault. The goal was to probe German coastal defenses, gather intelligence, and demonstrate Allied offensive capability. Instead, the operation collapsed almost immediately. German forces occupied elevated positions along steep white cliffs overlooking the port. Concrete bunkers concealed machine guns and heavy weapons that commanded every approach. As Allied soldiers landed, they were met with relentless, overlapping fire. Waves of infantry were cut down before they could reach cover. 27 Churchill tanks attempted to support the assault. None succeeded. Some were disabled by obstacles, others destroyed by anti-tank fire. The remainder were abandoned on the beach. By the end of the day, the scale of the disaster was undeniable. Of the 4,963 Canadian troops who embarked that morning, fewer than half made it back to Britain. Casualty figures were staggering: 3,367 Canadian losses, including 916 killed and nearly 2,000 taken prisoner. The Royal Navy suffered over 300 men killed, missing, or captured. The Royal Air Force lost 62 aircraft and pilots in desperate air battles above the coastline. German casualties, by comparison, remained below 600. The entire operation, from first landing to final evacuation, lasted less than 9 hours. Those 9 hours reshaped Allied thinking. Dieppe demonstrated with brutal clarity that attacking a fortified port head-on was effectively suicidal. German defenses were not improvised, they were meticulously designed. Thick concrete casemates shielded artillery from naval bombardment. Machine gun nests were positioned to create lethal crossfires. Port infrastructure had been pre-rigged for demolition, ensuring that even a successful seizure would yield nothing usable. Major General John Hamilton Roberts, commander of the Canadian 2nd Division, later summarized the failure in a post-operation report uncovered decades afterward in Britain's National Archives. His assessment was blunt. German port fortifications, he wrote, were far stronger than intelligence had predicted. Naval gunfire proved ineffective against reinforced emplacements. Infantry assaults faced uninterrupted fire from every angle. Even if the port had fallen intact, German reserves would likely have retaken it within 2 days. The implications were unavoidable. To invade continental Europe, the Allies required a functioning harbor to land vehicles, ammunition, fuel, and reinforcements at scale. Yet every major port along the Atlantic coast, from the Arctic north to the Bay of Biscay, had been transformed into a fortress layered with steel, concrete, and firepower. The strategic dilemma was complete. Europe could not be invaded without ports. Ports could not be captured without unacceptable losses. And so what once sounded ridiculous inside a Whitehall conference room began to look less like folly and more like necessity. By the final months of 1943, Adolf Hitler's long-touted Atlantic Wall was no longer just a slogan. Its transformation into a tangible defensive system began in earnest after Field Marshal Erwin Rommel was appointed Inspector General of the Atlantic Coastal Defenses. Rommel, already famed for his aggressive battlefield instincts, approached the task with urgency and skepticism. After completing an intensive inspection tour that lasted roughly 2 weeks, Rommel submitted a classified evaluation that painted a grim picture. Preserved today in German military archives, his report made clear that the defenses lacked any coherent strategic doctrine. Existing preparations, he warned, bore little resemblance to what would be required to stop a large-scale amphibious invasion. In his view, Germany was dangerously unprepared. Rommel's response followed his characteristic logic: act immediately, act forcefully, and act everywhere at once. He ordered the rapid deployment of millions of landmines along likely invasion beaches. He demanded reinforced concrete strongpoints at all tactically significant locations. Beach obstacles were installed under his personal supervision, steel and timber structures intended to tear open the hulls of landing craft before troops could disembark. Behind the beaches, fields were filled with what soldiers came to call Rommel's asparagus, tall wooden poles driven into the earth at angles, their sharpened tips designed to smash gliders and kill airborne troops before they reached the ground. These measures reflected Rommel's belief that the invasion had to be destroyed at the shoreline or not at all. Perhaps most consequential for Allied planners was his decision to prioritize port defenses. In a confidential memorandum sent to Hitler on December 31, 1943, Rommel argued that any Allied landing would likely concentrate against the sector held by the German 15th Army. He reasoned that the enemy's overriding objective would be the rapid seizure of a deep-water port capable of servicing large cargo vessels. Hitler embraced this assessment and designated 11 key ports as fortress harbors to be defended without retreat. These included Dunkirk, Boulogne, Le Havre, Cherbourg, Saint-Malo, Brest, Lorient, Saint-Nazaire, the Gironde estuary leading to Bordeaux, and the Channel Islands. Each location received priority access to manpower and materials. These fortresses were formidable. Heavy naval guns were encased in massive concrete emplacements. Artillery batteries covered every possible approach by land and sea. Anti-aircraft defenses formed layered protective zones. Minefields stretched for miles beyond the ports into surrounding countryside. Garrisons were explicitly ordered to fight until annihilation if necessary. Underlying all German defensive planning was a belief so deeply ingrained that few senior officers ever questioned it. No invading army could survive without quickly capturing a major port. Without such a facility, supply shortages would doom the operation within days or weeks. This assumption had governed warfare for centuries. Armies required sheltered harbors for transport ships, docks for repairs, cranes to unload heavy equipment, warehouses for storage, and protection from storms capable of wrecking entire fleets. On the Allied side, this reality was understood just as clearly. General Dwight D. Eisenhower, appointed Supreme Commander of the Allied Expeditionary Force, wrestled with the dilemma long before the invasion began. In a diary entry from March 1943, he summarized the problem with blunt clarity. Assaulting a fortified port would mean horrific casualties. Landing on open beaches would risk logistical collapse. Either option, on its own, appeared fatal. Yet Eisenhower hinted at a third possibility, one born from earlier failures and unconventional thinking. That idea had been quietly developing among British engineers even before the disastrous Dieppe raid. Its intellectual origins reached back to the First World War. In 1917, Winston Churchill, then serving as First Lord of the Admiralty, had proposed an untested concept, creating artificial harbours using prefabricated structures and flat-bottomed vessels to support operations against enemy-held coastlines. The war ended before the idea could be realised, but Churchill never abandoned it. In the spring of 1942, during a conference addressing the impossibility of seizing a defended port, Churchill revived the concept. According to multiple eyewitness accounts, his response stunned the room. If existing ports could not be taken, he declared, then the Allies would bring their own ports with them. The proposal bordered on the unbelievable. How could a harbour large enough to sustain an invasion army be constructed from scratch? How could enormous quantities of concrete and steel be transported across the English Channel? How could such structures be assembled under enemy fire, anchored securely to the seabed, and survive tides that rose and fell by nearly 20 feet? How could they endure the violent storms common to Channel waters? Each question generated a cascade of technical challenges. But the strategic necessity was undeniable. On May 30, 1942, Churchill issued a brief but decisive directive to Admiral Lord Mountbatten. The order, just 60 words long and preserved in the War Office archives, demanded floating piers for use on open beaches, capable of rising and falling with the tide. The anchoring problem, Churchill insisted, must be solved. Debate was unnecessary. The obstacles would reveal themselves soon enough. Mountbatten responded by assembling a multidisciplinary team of Britain's most accomplished engineers, naval architects, and construction experts. Their early meetings at the Institution of Civil Engineers in Westminster underscored the magnitude of the task. What was being asked seemed to defy both engineering precedent and common sense. Lieutenant General Frederick Morgan, Chief of Staff to the Supreme Allied Commander, and his COSEC planning staff calculated the operational requirements. The artificial harbours would need a throughput comparable to the port of Dover, the busiest cross-channel hub in Britain. They would have to unload at least 12,000 tons of supplies every day, regardless of weather. They needed to accommodate vessels ranging from small landing craft to Liberty ships displacing over 10,000 tons. They had to provide safe anchorage in seas reaching force 6 on the Beaufort scale. And most critically, they had to be operational within days of the initial landings. The technical specifications alone ran to hundreds of pages. Between June and August 1942, civil engineer Hugh Iris Hughes, a Welsh specialist with deep experience in harbour construction, submitted detailed proposals to the Royal Navy. These plans would become the foundation of one of the most audacious engineering achievements of the Second World War. The concept drew upon nearly 100 years of accumulated experience in harbour construction. Every success, failure, and improvisation from past port projects was studied and distilled into a single, unprecedented design. While the overall vision came from one central plan, its execution relied on the expertise of numerous engineers, each responsible for a critical piece of the puzzle. Among them was Lieutenant Alan Beckett of the Royal Engineers, who devised an innovative system of articulated steel roadways. These floating causeways were engineered to flex vertically with changing tides, ensuring that vehicles and supplies could move continuously between ship and shore regardless of sea level. At the same time, naval architects proposed an equally unconventional solution for wave protection. Aging merchant vessels, no longer fit for service, would be deliberately sunk in carefully calculated positions to form temporary breakwaters. The boldest idea of all involved enormous hollow concrete structures, later known as caissons. These vast floating chambers would be constructed inland, towed across the English Channel, and then deliberately submerged in formation to create a solid barrier against the sea. No project of this scale had ever been attempted, let alone under wartime conditions. In October 1942, these ideas were formally presented at a combined operations meeting in Scotland, codenamed Operation Rattle, held at Largs. Commodore John Hughes Hallett and Royal Navy Captain Tom Hussey laid out the full proposal before a room filled with senior military planners. Their briefing stretched on for 4 hours, delving into every conceivable detail from tidal behavior and wave dynamics to the precise chemical composition of the concrete required to withstand constant pounding by the sea. the initial response was far from enthusiastic. Doubt filled the room, particularly among the American delegation. According to the official minutes, a U.S. Navy officer identified only as captains gave voice to the prevailing concern. He summarized the plan with biting clarity. The Allies were being asked to build something comparable to a major commercial harbor, dismantle it into countless components, transport those parts across one of the most heavily defended waterways on Earth, reassemble everything under enemy fire, and have it fully operational in a matter of days. After a quarter century at sea, he concluded, this was the most unrealistic proposal he had ever heard. Hughes Hallett's reply, preserved word for word in the transcript, reflected the grim reality facing Allied strategists. He openly acknowledged that the plan violated established rules of harbor engineering, depended on technologies still in their infancy, and required industrial output that might stretch Allied capacity to its limit. Yet, he argued, the alternatives were even bleaker. Without a way to land and sustain massive forces on the European coast, any invasion was doomed before it began. The choice, he said, was not between a sensible plan and a reckless one, but between attempting the impossible or abandoning the invasion entirely. What finally shifted opinion was not another calculation or blueprint, but a simple, improvised demonstration. Commander Robert Grant used the conference room sink as a makeshift test basin. Paper cutouts stood in for transport ships, while a hairbrush was used to agitate the water and simulate rough seas. Without protection, the miniature fleet quickly overturned. Grant then placed an inflated lifebelt of the type worn by aircrews into the sink, representing a breakwater. This time, when waves were generated, they struck the barrier instead. The paper ships behind it remained upright. The display was unsophisticated and almost playful, yet its message was unmistakable. Calm water meant ships could survive. Ships that survived could unload supplies. And sustained supply was the foundation of any successful campaign. The proposal advanced to the highest level of Allied leadership in August 1943, when Winston Churchill and President Franklin D. Roosevelt met in Quebec alongside the combined chiefs of staff. Churchill himself introduced the artificial harbor concept, framing it with the theatrical confidence for which he was famous. According to the official record, he described a plan of staggering ambition: the construction of 2 complete harbors in secret, their transport across the channel, and their assembly on enemy-held beaches, all under constant risk of discovery. The Germans, Churchill asserted, would dismiss such an undertaking as fantasy. That disbelief, he suggested, would be the Allies' greatest advantage. Franklin D. Roosevelt grasped the implications of the proposal almost instantly. His earlier experience as Assistant Secretary of the Navy had given him more than political familiarity with engineering. It had trained him to recognize the scale and difficulty of complex technical undertakings. He understood not only the mechanical obstacles involved, but also the overwhelming strategic importance of success. The plan was then subjected to intense scrutiny by the combined chiefs of staff. For 48 hours, senior military leaders dissected every component of the concept. They evaluated the strength of reinforced concrete needed to withstand open sea conditions, studied tidal cycles along the Normandy coast, and calculated the firing ranges of German coastal batteries. No variable was considered too small. On September 2, 1943, the deliberations concluded. The combined chiefs formally endorsed the project, estimating that the proposed artificial harbors would need the capacity to unload approximately 12,000 tons of supplies every day, regardless of weather conditions. This figure did not even include vehicle traffic, underscoring the extraordinary logistical expectations placed upon the design. Just 2 days later, on September 4, official authorization was granted to begin immediate construction. Yet, before a single structure could be built, bureaucratic conflict threatened to cripple the initiative. A bitter dispute erupted between the War Office and the Admiralty over who would control the project. The Admiralty argued that any structure capable of floating fell unequivocally under naval authority. The War Office responded that harbor construction, regardless of buoyancy, was fundamentally an Army engineering responsibility. This institutional struggle dragged on for nearly 3 months. Endless meetings consumed valuable time while crucial decisions were repeatedly postponed. The stalemate was finally broken on December 15, 1943, when the Vice Chiefs of Staff stepped in and imposed a binding compromise. Under the final arrangement, the Admiralty assumed responsibility for the blockships that would be deliberately sunk to form inner breakwaters, as well as for the outer floating and bombarded breakwaters. Naval authorities would also oversee assembly operations along England's southern coast, conduct surveys of the French shoreline, mark navigational channels, and tow every major component across the English Channel. The War Office, in turn, was tasked with constructing the massive concrete caissons, code-named Phoenix, and the floating roadways known as Whale. The Army would also provide anti-aircraft defenses during assembly. Once deployed off the French coast, Army engineers would sink the caissons into position and complete the final harbor installations. With responsibilities clearly defined at last, the project could move forward. What followed was a construction effort unlike anything Britain had ever attempted. Beginning in the summer of 1943, work accelerated rapidly across dozens of sites. At its peak, as many as 45,000 workers were engaged simultaneously. The Phoenix caissons themselves represented a triumph of wartime engineering. The largest units stretched nearly 200 feet in length, stood 60 feet high, and weighed over 6,000 tons when fully completed. In total, 213 caissons of varying dimensions were required. Their production consumed more than 1 million tons of reinforced concrete and approximately 70,000 tons of steel reinforcement resources that were already scarce under wartime conditions. To accommodate construction, vast sections of land were excavated along the Thames and Medway rivers. These excavations became temporary dry docks where the caissons could be assembled. Each Phoenix unit was essentially a gigantic hollow concrete structure, sealed airtight except for carefully engineered flooding valves. These valves allowed engineers to sink the caissons gradually and precisely onto the seabed once in position. Design tolerances were unforgiving. The walls needed to be thick enough to resist violent Atlantic storms, yet light enough to remain buoyant during towing. Steel reinforcement had to be placed with exacting precision to prevent cracking or collapse under stress. Concrete mixing, pouring, and curing all had to meet strict standards despite shortages of materials and relentless time pressure. The workload was distributed among many of Britain's leading commercial construction firms. Companies such as Waits Construction, Balfour Beatty, Henry Boot, Bovis, Costain, John Lang & Son, Peter Lind & Company, Sir Robert McAlpine, Mowlam, Nuttall, and Taylor Woodrow each built individual sections. Secrecy was absolute. Workers were deliberately kept unaware of the ultimate purpose of what they were building. Each team knew only its immediate assignment. The broader vision remained hidden. Decades later, in a 1970 interview, Arthur Waits, managing director of Waits Construction, reflected on that period. He recalled that his workforce had assembled enormous concrete pontoons strictly according to government specifications, without any explanation of their intended use. Among the men, rumors circulated that the structures were somehow connected to post-war housing projects. When a senior official from Whitehall toured the construction yards and noticed the confusion, he offered only reassurance. The work, he said, was of critical importance to the war effort. It was not until after the landings in Normandy that the truth became known. Only then did the builders realize they had been constructing the foundations of the artificial harbors that made D-Day possible. Constructing floating roadways presented engineers with a unique set of technical challenges. Alan Beckett's approach involved creating bridge spans 80 feet in length, mounted atop floating pontoons referred to as beetles, which were made from either steel or concrete. The design required a careful balance. The structures needed sufficient flexibility to absorb tidal fluctuations reaching up to 20 feet, while remaining sturdy enough to carry fully loaded trucks. The solution came in the form of torsionally flexible joints, allowing each span to rotate independently yet still form a continuous driving surface. Plans called for 16 kilometers of these specialized roadways, each unit precisely engineered to link seamlessly with its neighbors. The docking platforms, where ships would eventually moor, were assigned the code name Spud. Each spud consisted of a large pontoon supported by 4 legs resting on the seabed, enabling the pontoon to rise and fall with the tide. Hydraulic mechanisms permitted the legs to extend or retract, maintaining a consistent deck height relative to docked vessels. The engineering tolerances for these systems were remarkably exacting fractions of an inch across components weighing hundreds of tons. Testing proved to be a vital part of the development process. A secluded Scottish harbour at Garriston in Wigtown Bay, featuring flat sandy terrain and limited population, provided conditions closely resembling the Normandy beaches. The area was placed under strict security measures, with locals evacuated under wartime regulations. From Garriston to the nearby area of Warner, the site was declared off-limits. A military camp at Cad housed hundreds of engineers and support staff who conducted the trials and refined the Mulberry system components. The testing phase exposed numerous design flaws that, if left undiscovered, could have led to catastrophic failures on D-Day. Early models of floating roadways collapsed under the weight of a 7-ton truck when exposed to realistic wave conditions. Flexible Swiss roll-style roadways were completely destroyed during a severe storm at the test site. Hippo-type pontoons became destabilized in the sandy seabed, causing their associated bridge spans, dubbed crocodile bridges, to fail structurally. Beckett's whale design, however, remained intact after the storm, securing its selection for the final harbour structures. The floating breakwaters, called bombardons, initially constructed from steel and rubberized canvas, also underwent significant modifications following early test failures. Original plans had used hemp ropes to connect the units, but storms caused the ropes to snap, allowing the massive structures to drift, which would have posed a grave risk to the harbour. Redundant steel cable connections replaced the ropes, providing a much more secure and reliable solution. Security surrounding the project was extreme. The name Mulberry was deliberately chosen to convey no information about its purpose. It was simply the next unused designation in a sequence of arbitrary code names. All correspondence referred only to Mulberry, never mentioning floating harbors or artificial ports. Workers were required to sign official secrecy agreements, and photography of the components was strictly forbidden. Intelligence services monitored local pubs near construction sites, ensuring no casual conversation might reveal sensitive information. German reconnaissance flights over southern England represented a constant risk. The largest components, known as Phoenix units, were impossible to conceal once assembly began. To cover their purpose, officials claimed they were experimental anti-submarine barriers for deployment in the English Channel. German intelligence apparently accepted this explanation, as no specific countermeasures were taken against artificial harbors. A near-catastrophic security lapse occurred in May 1944, weeks before the invasion. The Daily Telegraph published a crossword puzzle containing clues that led to answers directly associated with Operation Overlord. Over consecutive days, solutions included the code names of the 5 invasion beaches: Utah, Omaha, Juneau, Sword, and Gold, as well as Mulberry itself. MI5 quickly investigated the compiler. Leonard Dorr, headmaster of a local school. Interrogation revealed that Dorr frequently collected words suggested by his students, many of whom lived near U.S. military installations involved in invasion planning. The appearance of classified terms in the puzzle was deemed coincidental, albeit alarming. MI5 continued surveillance until after D-Day to confirm that no espionage had occurred. By June 1944, thousands of components were scattered across southern England, awaiting transport to assembly points, movement across the Channel, and final positioning along the Normandy coast, a logistical operation of staggering complexity. 2 fully functional artificial harbors had been completed. Mulberry A, intended to support American landings at Omaha Beach near St. Laurent-sur-Mer, and Mulberry B, prepared for use by British and Canadian forces. Each harbor was the culmination of meticulous engineering, extensive testing, and extraordinary secrecy. Mulberry B, later designated Port Winston in tribute to Winston Churchill, was planned to provide logistical support for British and Canadian forces landing at Gold Beach near Arromanches. The construction of each artificial harbor demanded immense quantities of building materials, including roughly 600,000 tons of concrete and prefabricated steel elements. The components consisted of 213 Phoenix caissons of varying dimensions, 10 miles of floating whale roadway units, 33 pierheads, 70 decommissioned merchant ships intended for scuttling to form additional breakwaters codenamed gooseberries, and 24 enormous floating bombard breakwaters designed to shield the outer perimeter. Transporting this unprecedented artificial fleet required 150 ocean-going tugs, all modified for extended distance towing. These vessels were marked by large insignias painted on their funnels, a source of pride for crews who understood they were contributing to one of the most ambitious engineering undertakings in military history. The towing operations themselves were highly complex. Each Phoenix caisson had to be towed at a maximum speed of 4 knots to avoid structural damage, and the voyage from assembly points in England to the Normandy coastline would take approximately 2 days under optimal conditions. Weather forecasts were critical. Heavy seas could jeopardize both the integrity of the caissons and the tow lines. Additionally, the tugs navigated through waters laden with naval mines while maintaining formation within large convoys. Royal Navy minesweepers preceded the convoys, clearing safe passages through minefields laid months earlier. On June 4, 1944, the first deployment orders for the Mulberry Harbour units were issued. Sections of the harbours began their journey behind the tugs, positioned in mid-channel to await the planned invasion on June 5. However, a violent storm swept across the English Channel, delaying the operation. The floating harbour components endured 24 hours of turbulent seas while Eisenhower weighed the decision to proceed. Ultimately, he authorized the launch of Operation Overlord on June 6, and by then, the harbour units were already en route to the beaches. In the pre-dawn hours of D-Day, as Allied forces landed under intense German resistance, the initial sections of Mulberry B were being carefully maneuvered into their designated positions. On June 7, D-1, the first Phoenix caissons were positioned approximately 1 mile offshore from Omaha and Gold beaches. Powerful harbour tugs guided the massive concrete structures with surprising precision, placing them according to coordinates marked by buoys previously deployed by Royal Navy survey ships. Each caisson was engineered with multiple chambers and individual flood valves, allowing engineers to selectively fill sections to adjust orientation and achieve exact placement before settling the structure on the seabed. This meticulous process required hours for each caisson, but ensured the formation of secure, sheltered waters suitable for anchoring supply ships. Simultaneously, 70 obsolete merchant vessels were moved into predetermined positions for scuttling. Known as the Gooseberry Breakwaters, these ships had been gathered on Scotland's west coast months prior. Stripped of valuable equipment, ballasted for accurate buoyancy, and fitted with scuttling charges, they completed their final voyage under their own power. Upon reaching assigned coordinates, crews activated the charges and abandoned the ships. These vessels sank to the seabed in carefully calculated locations, forming an outer barrier against Atlantic swells. At Utah Beach, 10 ships including the Benjamin Conti, David O. Sailor, George S. Wilson, and Victory Sword were scuttled. At Omaha Beach, another formation of Gooseberry ships established the outer protective perimeter. Remarkably, most vessels settled within 50 feet of their intended positions, a testament to the precision of the operation. Following the scuttling, the whale roadway units were deployed. Long assemblies of linked pontoons and bridge spans were towed across the channel by specialized tugs. Once in position, Royal Engineers anchored them to the pierheads and extended the roadways toward the shore. The flexible joints, designed by engineer Beckett, allowed the structures to move with the waves while maintaining integrity. By June 13, Mulberry B at Arromanches had become operational, providing 2 crescent-shaped harbours capable of accommodating up to 75 Liberty ships along with smaller vessels simultaneously. The rapid construction astonished even the planners. Within a week of the D-Day landings, both artificial harbours were actively receiving cargo. Supply ships that arrived encountered facilities that had not existed 10 days earlier, including floating piers, breakwaters, and navigational markers. Captain James Morrison of the Liberty ship Robert E. Perry recorded in his log, "Approached an area charted as open beach, only to find fully functional harbour facilities with floating piers and breakwaters. docked at Pier 7 of Arromanches Harbour and discharged 400 tons of ammunition, 200 tons of rations, and 150 vehicles in 8 hours. The harbour rises and falls with the tide by 15 feet but remains completely operational throughout. The execution of Mulberry B showcased not only remarkable engineering ingenuity, but also the extraordinary coordination and planning that made the Normandy landings feasible. Within days, these artificial harbours transformed a stretch of coastline into a fully functioning supply hub, critical to sustaining the momentum of the Allied invasion. The engineering behind these structures was astonishing, pushing the limits of contemporary construction and initially almost beyond comprehension. Yet the ingenuity of these artificial harbours would soon face an extreme test. On June 19, 1944, the English Channel was struck by an unprecedented storm, the most severe June tempest in 4 decades. For 3 continuous days, fierce northeasterly winds ranging from force 6 to force 8 on the Beaufort scale lashed the Normandy coastline. Waves soared up to 8 feet, relentlessly battering the man-made harbours. The bombard and outer breakwaters, designed to absorb the brunt of such assaults, began to fail under the relentless pounding. Some segments fractured entirely, while others were torn from their moorings and carried into the inner harbour areas, colliding violently with Phoenix caissons and sections of the floating whale roadways. At Omaha Beach, Mulberry A bore the worst damage. The harbour had not been fully completed when the storm hit. Critical reinforcements and anchoring systems were still in the process of installation. As a result, Phoenix caissons cracked under the wave impact, and whale roadways broke loose, washing ashore in a tangled mass. By the time the storm finally subsided on June 22, Mulberry A had been rendered unusable. The American command made the swift decision to abandon the harbour. Assessments revealed that repairing it would take longer than constructing a new facility, as the damaged components first required careful removal. Instead, salvageable sections were recovered and sent to strengthen Mulberry B at Arromanches. Meanwhile, the British harbour, benefiting from more natural protection at Gold Beach and having been completed before the storm, sustained damage but remained operational. Reinforcements from the American harbour were incorporated into Mulberry B, and the Phoenix caissons were filled with sand to improve their stability and adjustment that contributed to the harbour's unexpectedly long service. The storm, though destructive, ultimately validated the Mulberry harbour concept. At Omaha Beach, where Mulberry A had been destroyed, the Gooseberry breakwater constructed from deliberately sunk ships remained intact. The waters behind this barrier provided crucial shelter, allowing vessels anchored there to withstand the storm with minimal damage. Without even this rudimentary protection, the storm could have dispersed the invasion fleet and jeopardized the entire operation. Lieutenant Colonel George Shattuck, who commanded the 20-port group Royal Engineers overseeing Mulberry B, noted in his after-action report, "From June 19 to 22, our harbour was subjected to forces far exceeding its design specifications. That any element survived is a testament to the quality of British engineering and foresight of our planners. The breakwaters that failed did so while absorbing energy that would have otherwise destroyed the entire invasion fleet. Even in its partial failure, the Mulberry concept proved invaluable." The destruction of Mulberry A forced American troops to rely on direct beach landings of supplies, a method they soon perfected with remarkable efficiency. By early July, despite the absence of a functional harbour at Omaha, supply operations were delivering 12,000 tons daily, surpassing expectations. The Gooseberry breakwater remained critical to this success. At Arromanches, Mulberry B continued to operate far beyond its intended lifespan. Originally designed to function for merely 3 months, enough to secure and reopen the port of Cherbourg, the harbour, later called Port Winston, remained active for 10 months following D-Day. The operational achievements of a single artificial harbour were staggering. Through Port Winston, 2.5 million troops, 500,000 vehicles, and 4 million tons of supplies passed. At its peak, the harbour handled 7,000 tons of equipment daily, operating continuously around the clock. The whale roadways, initially intended to last 3 months, endured 10 months of near-constant use. Fully loaded trucks travelled directly from Liberty ships to the French shoreline via floating bridges. Many of these spans were salvaged after the war, repaired and repurposed to replace bombed bridges throughout France, Belgium, and the Netherlands. Surviving examples can still be seen today, such as a bridge over the Loire River in Normandy and another crossing the Moselle River between Cattenom and Königsmacher. The German reaction underscored a profound failure in both intelligence and strategic planning. German commanders had assumed the Allies would need to capture an established port and had heavily fortified Cherbourg, Le Havre, and other ports accordingly. The Atlantic Wall, reinforced with millions of mines and thousands of concrete bunkers, was primarily concentrated around these port facilities. When the landings occurred on open beaches rather than at ports, German intelligence initially interpreted it as a limited raid rather than a full-scale invasion. Even as the true scale became apparent, they assumed the Allies would quickly advance to seize Cherbourg. The introduction of artificial harbors near the invasion beaches astonished the German High Command. They had no prior knowledge of the Mulberry project, and its scale contradicted their assumptions about military feasibility. This disbelief afforded the Allies vital time to establish and consolidate the beachhead. Albert Speer, Nazi Germany's Minister of Armaments and War Production, would later acknowledge the significance of these harbors. In post-war interrogations and his memoirs, he reflected on the failure of the Atlantic Wall. To construct our defenses in 2 years, we used 17 million cubic meters of concrete and 1.2 million tons of steel. Yet, just a fortnight after the enemy landings, this monumental effort was undone by an idea of extraordinary simplicity and genius. The concept he referred to was the Mulberry harbor system, a decisive factor in the success of the Normandy invasion. Germany poured vast resources into reinforcing every key port along the Atlantic coastline. The Nazi High Command assumed that these fortifications would render any Allied landing extraordinarily costly, if not outright impossible. Yet, rather than confront these defenses head-on, the Allies sidestepped them entirely, deploying their own portable harbor systems. This approach was more than a clever tactical maneuver. It revealed a deep divergence in strategic thought between the two sides. German planning remained anchored in the defensive doctrines of the 19th century, emphasizing fortified positions and the rigid defense of strongpoints. In contrast, the Allies embraced adaptive thinking, often attempting solutions considered impractical or unattainable by conventional military wisdom. This contrast was evident not only in the innovative harbor operations but in the overall Allied strategy. Germany depended heavily on static fortifications and reactive armored counterattacks, whereas the Allies invested in specialized technologies designed to overcome natural and man-made obstacles. One striking example of this ingenuity was Hobart's Funnies, a fleet of highly modified tanks. These included flail tanks for clearing minefields, bridge-laying tanks for crossing difficult terrain, and amphibious tanks capable of swimming ashore. Germany possessed impressive technical breakthroughs such as the V-2 rocket and jet aircraft, but these innovations could not be scaled into decisive advantages due to industrial limitations and rigid strategic thinking. The Allies, particularly Britain and the United States in partnership, paired technical creativity with mass production, turning experimental designs into operational capabilities. The improvised Mulberry harbors illustrated this synergy of invention and industrial capacity. Engineering solutions range from Beckett's flexible floating roadways to the Phoenix Caisson's massive prefabricated concrete units designed to control coastal flooding and provide docking platforms. The success of these projects depended on Britain's ability to manufacture and coordinate production on a scale rarely seen even amid 4 years of total war. At the height of construction, over 45,000 workers labored simultaneously, supported by numerous commercial firms that redirected resources from other wartime production efforts. Coordinating this massive endeavor demanded unprecedented collaboration between government ministries, military branches, and private industry. The Phoenix Caissons alone posed a monumental challenge. 213 colossal reinforced concrete structures, each weighing thousands of tons, had to be produced and transported. The project required more concrete than most countries could produce in an entire year, and construction sites had to be established along riverbanks from scratch. Materials, cement, steel, and aggregates had to be carefully allocated despite widespread shortages. Transporting the caissons to the assembly points was equally daunting. Specialized handling equipment and meticulous scheduling were essential to ensure every unit could withstand ocean towing and stormy conditions. Moving roughly 600,000 tons of concrete and steel across 30 miles of open water demanded naval precision. The operation involved 150 tugs, representing a significant portion of Britain's fleet, many of which were commercial vessels repurposed for military duty. Crews had minimal training in towing oversized loads through mined waters, yet remarkably few caissons were lost, and most damage resulted from severe weather rather than enemy action. The human effort behind Mulberry was as extraordinary as the technical feats. Colonel V.C. Steer Webster, a Royal Engineer, played a pivotal role in designing, testing, and implementing the entire suite of Mulberry equipment. His detailed diaries, now preserved at McMaster University in Canada, provide insight into the immense pressure faced by engineers in the lead-up to D-Day. On March 15, 1944, he noted Churchill's personal inspection of the floating roadway, testing its capacity to carry fully loaded vehicles. By April 3, 1944, he documented the discovery of cracks in 2 caissons, traced to incorrectly placed reinforcing steel, and the urgent need to inspect all units to prevent delays to the invasion. By May 20, 1944, his entries reflected the relentless pace, long hours, and near-constant stress of preparing one of the most ambitious engineering projects in wartime history. The Mulberry harbors exemplify how strategic innovation, industrial might, and meticulous organization can combine to overcome formidable defenses. While Germany relied on static fortresses and reactive tactics, the Allies leveraged creativity, flexibility, and scale, turning technological ingenuity into decisive operational advantage. The project remains a testament not only to engineering brilliance but also to the human effort, coordination, and persistence required to translate vision into reality under the pressures of war. Final preparations are in full swing, and the scale of the undertaking defies comprehension. Had anyone outlined this project to me 3 years ago, I would have dismissed it as utterly unachievable. Yet now, standing on the brink of operation, we have transformed what once seemed impossible into something imminent and tangible. Failure, should it occur, would bring catastrophic consequences. First-hand accounts from the engineers who managed the Mulberry harbors in France provide an invaluable perspective on the magnitude of this achievement. Sapper William Hutchinson, serving with the 20 Port Group, described his experience in a letter home in July 1944. "Our days stretch to 18 hours as we keep Port Winston running," he wrote. "The harbor functions like a living machine, rising and falling 15 feet with every tide. We are constantly adjusting moorings, inspecting floating pontoons for damage, repairing sections of roadway, and guiding ships to their designated berths. German artillery occasionally targets us from inland, and Luftwaffe air raids occur nightly, yet the flow of supplies never halts. Today alone we unloaded 40 vessels carrying tanks, ammunition, rations, fuel, and medical equipment. Everything an army requires passes through this floating port." Reflecting on the fact that this entire facility did not exist a month ago, and that we assembled it under fire from components towed across the channel, I can hardly believe I am part of it. The crews of merchant ships who delivered supplies to Port Winston were equally astonished. Captain Robert Fraser, commanding the Liberty ship John P. Holland, submitted a report after completing his 3rd voyage to Arromanches. "We approached the French coast expecting to anchor offshore and transfer cargo to the beach in smaller craft, as is standard at unimproved harbors. Instead, we were directed straight to Pier 11 in Port Winston. The harbor, composed of breakwaters, floating piers, and navigational aids, was as substantial and stable as any permanent port I've docked at in 20 years at sea. The engineering feat required to construct this harbor from scratch, secure it against tides and storms, and operate it under combat conditions is extraordinary. We discharged 500 tons in 6 hours before moving aside for the next ship. Its efficiency rivaled the operations of peacetime ports. The impact of the Mulberry harbors on the Normandy campaign cannot be overstated. Without these floating facilities, the Allies faced 3 grim alternatives. 1. To attempt an immediate assault on a fortified port such as Cherbourg, risking massive casualties at a time when Allied forces were still vulnerable and German defenses were strong. 2. to rely exclusively on beach landings, which left the supply chain at the mercy of weather that could easily have wrecked the entire invasion, as demonstrated by the severe storm in June. 3. To postpone the operation indefinitely while searching for a viable alternative which might not exist. The Mulberry solution eliminated these dire choices. It provided harbor capacity equivalent to a major port without the human cost of a direct assault or the vulnerability of open beaches. The harbors processed enough tonnage to sustain the buildup of forces in Normandy during the critical early months. By the time American forces captured Cherbourg on June 26, 1944, the immediate logistical crisis had passed. Even after German demolition rendered Cherbourg unusable for several weeks, the advance continued unhindered thanks to the uninterrupted supply line maintained through Port Winston. The strategic significance of these harbors extended beyond Normandy. Their success prompted a profound shift in Allied amphibious doctrine. After D-Day, planners no longer operated under the assumption that capturing a port immediately was a prerequisite for sustaining operations ashore. The Mulberry harbors demonstrated that it was possible to construct and maintain fully operational logistics hubs under fire, fundamentally redefining the approach to large-scale amphibious invasions. Future amphibious operations could be launched on any beach deemed suitable thanks to the development of artificial harbor systems capable of sustaining military activity until permanent ports could be captured and restored. This flexibility gave the Allies an unprecedented strategic advantage in selecting landing sites. Instead of being constrained to locations near existing harbors, commanders could choose beaches based on weak points in enemy defenses. German forces, aware of this capability, could no longer concentrate their defenses solely around key ports, fearing Allied landings could occur anywhere along thousands of miles of coastline. This strategic uncertainty compelled the German military to disperse their forces widely rather than massing them at critical points, diluting their effectiveness. Allied planners began adapting Mulberry-style harbor technology for the potential invasion of Japan, dispatching engineers to the Pacific to survey beaches and determine what construction would be necessary. However, the deployment of atomic bombs on Hiroshima and Nagasaki in August 1945 made these invasion preparations unnecessary. Nevertheless, the detailed planning highlighted how fully the Allies had integrated Mulberry harbor concepts into their operational doctrine. No wartime engineering effort of similar scale or ambition has been undertaken since 1944. The project's uniqueness lay in its combination of technical ingenuity, large-scale industrial production, operational security, logistics, and the ability to deploy under combat conditions. Modern military analysts studying amphibious assaults still examine the Mulberry harbors as a prime example of how engineering solutions can overcome seemingly impossible tactical problems. The remains of Port Winston can still be observed today at Normandy, where the Phoenix caissons are visible at low tide and serve local fishermen as navigational markers. Visitors to the D-Day beaches can witness concrete evidence of what Allied engineers accomplished in a remarkably short time frame. Similar structures are scattered along the British coastline, standing as reminders of the trial and error involved in wartime construction. At Pagham Harbour in West Sussex, a caisson known as the Near Mulberry sank during towing and could not be refloated, now protected as a historic monument visible during low tide. Another, called the Far Mulberry, fractured in a storm the night before D-Day and rests in deeper water offshore. At Thorpe Bay near Southend-on-Sea, a caisson being transported from Immingham to Southsea developed a leak and was deliberately beached on a sandbank in the Tenham estuary, later recognized as a scheduled monument and accessible to determined visitors at low tide. These preserved failures underscore the inherent risks of the Mulberry project. Not all components functioned as intended, and not every caisson reached Normandy intact. A storm in June destroyed one complete harbor and severely damaged another. Yet the initiative succeeded because engineers from Britain and the United States incorporated redundancy, devised multiple solutions for critical problems, and adapted quickly when initial designs failed. The long-term effects of the Mulberry harbors extend beyond military history, influencing civil engineering and peacetime construction. Technologies originally developed from Mulberry, such as floating bridge systems inspired by Beckett's whale designs, advanced significantly due to wartime necessity. Lessons learned regarding breakwater construction and tidal adaptation informed post-war harbor design. Concrete mixing and curing techniques refined under urgent wartime conditions improved commercial construction practices worldwide. Perhaps most importantly, the project demonstrated that massive infrastructure could be completed in months rather than years when urgency demanded it. Planning, coordination, and execution skills honed during the harbor construction shaped post-war civil engineering projects globally. After the war, the engineers who built the artificial harbors carried their expertise into civilian construction, influencing large-scale projects under tight constraints. Recognition of their achievements came slowly. Wartime secrecy kept details classified for many years. Most engineers, modest and unassuming by training, did not seek attention. Steer Webster's archival collection remained private until it was donated to McMaster University in 1976. Q. Iorris Hughes, a key figure in the harbor design, received no public honors during his lifetime. Alan Beckett, whose Whale roadways proved critical to the project's success, continued his career quietly in relative obscurity. It was only decades later that historians fully appreciated the scale of the accomplishment. In 2018, the Institution of Civil Engineers included the Mulberry harbors among 200 celebrated projects during its bicentennial, acknowledging the extraordinary combination of innovation, logistics, and engineering skill that had made the harbors operational in time for D-Day and forever altered the approach to amphibious warfare. Academic research has explored both the technical innovations and organizational strategies behind the project, while documentary films brought these achievements to a broader public. Military historians have emphasized that the success of D-Day rested as much on engineering ingenuity as on battlefield courage. The differing approaches of the Allies and the Germans to the invasion problem became particularly clear in the development of the Mulberry harbors. German planners opted for the predictable course: heavily fortify the port so that any attempt to seize it would be nearly impossible. The Atlantic Wall, with its massive concrete installations and intricate defensive structures, exemplified the German commitment to meticulous, conventional military methodology. In contrast, the Allies pursued a less obvious path. They aimed to render existing ports unnecessary by creating entirely new ones at strategic locations. Achieving this demanded a belief that seemingly impossible feats could be realized through coordinated engineering and industrial effort. It required commanders ready to allocate vast resources to an untested idea, engineers willing to challenge conventional wisdom, and construction laborers executing tasks whose ultimate purpose was initially beyond their comprehension. This contrast in mindset was a decisive factor in the outcome of the invasion. German military doctrine prized hierarchy, obedience, and reliance on tried-and-true methods. While this fostered excellence in execution, it imposed rigidity in strategic planning. When Allied operations deviated from German expectations, the command system struggled to respond effectively. Allied military culture, particularly the collaboration between British and American forces, prioritized adaptability, inventive problem-solving, and practical solutions. Although this approach sometimes led to inefficiencies or disorder, it enabled rapid adjustment to unforeseen challenges. Faced with obstacles that conventional methods could not overcome, the Allies consistently explored unconventional solutions. The Mulberry harbors serve as a tangible representation of this cultural divergence. A German commander confronting the challenge of Cherbourg would have calculated the required forces and accepted the inevitable casualties. In contrast, an Allied commander endorsed the creation of floating harbors that bypassed the problem entirely. In 1984, on the 40th anniversary of D-Day, surviving engineers who had contributed to the Mulberry harbors gathered in Arromanches to commemorate their work. The reunion brought together British and American participants, encompassing both military personnel and civilians, designers and laborers. Their recollections, documented by the Imperial War Museum, provide a comprehensive conclusion to the story of Mulberry. Sir Bruce White, who oversaw much of the construction, reflected at the reunion dinner, "We were young men tasked with what seemed impossible. We had to construct a harbor that could be assembled within days, float in open waters, endure Atlantic storms, and support far more cargo than a conventional port, all on sandy seabeds rather than solid rock." Every engineering principle we had learned suggested failure, yet the mission demanded success. So we focused on solving the problem rather than questioning its feasibility. We tested, failed, adapted, and tested again. We produced components on a scale that stretched Britain's industrial capacity. We towed massive floating concrete structures across mined waters. We assembled the harbour while under artillery fire, and ultimately, it functioned. Not flawlessly, Mulberry A was lost in a June storm, and constant repairs were needed, but the harbour operated effectively enough to keep Port Winston supplying the invasion forces. That extra time allowed the Allies to capture Cherbourg, a critical difference between victory and defeat. Alan Beckett, whose innovations with the floating roadways proved essential, offered his own account. As a young engineer in the Royal Engineers, I was assigned to create a roadway capable of supporting immense weight while floating over tidal variations of up to 15 feet. The requirements were simultaneously contradictory: flexibility to adjust to tides, rigidity to carry loaded trucks, durability to survive months in salt water, simplicity for rapid production, and transportability across the channel. Each challenge alone was formidable. Together they appeared insurmountable. I spent weeks experimenting with small-scale models. The solution came unexpectedly from observing a snake moving over sand, flexible at multiple points, yet maintaining continuous forward motion. The roadways required similar properties: rigid within each span, flexible at the joints. Once that principle was established, the detailed engineering naturally followed. Seeing those floating roadways still operational 10 months after D-Day, carrying loads far exceeding their original design, remains one of my proudest achievements. An American civil engineer who had contributed to the Phoenix project reflected on the monumental industrial effort behind it. While much attention has been given to the technological breakthroughs, he emphasized that the methods of production were equally remarkable. Over a span of 8 months, teams constructed 213 massive reinforced concrete units under conditions of extreme scarcity. Britain was engaged in a total war, and materials, cement, steel, timber, manpower, transportation were all urgently needed elsewhere. Yet, the Mulberry Initiative received priority because both Churchill and Eisenhower recognized its strategic significance. The logistical coordination required was extraordinary. Concrete mixes had to meet precise chemical and structural specifications. Steel components were fabricated and installed with millimeter-level accuracy. Dry docks were built from the ground up along rivers to accommodate the assembly of massive quays. Once complete, these docks were flooded to float multi-thousand-ton concrete units, which were then towed to designated positions without sustaining structural damage. Achieving all of this simultaneously at numerous sites while maintaining absolute secrecy and under nightly attacks by German bombers reflected the unparalleled dedication of every participant, from laborers to senior engineers. A Royal Navy officer, who commanded one of the tugs responsible for transporting Phoenix units, recounted the crossing to Normandy. The journey took 2 days at a maximum safe speed of 4 knots. His team towed Unit 47, one of the largest, weighing more than 6,000 tons. The towing cable, thick as an adult's arm, strained visibly under the weight. Navigation was conducted through channels cleared of mines marked by buoys which German E-boats frequently attempted to remove. Maintaining formation within a massive convoy, avoiding collisions, and coordinating thousands of vessels all moving toward the invasion beaches demanded constant vigilance. Upon reaching their assigned position off Omaha Beach, the crew held steady while engineers gradually flooded the Phoenix units in a controlled sequence, a process that required 6 hours to position each structure precisely. After completing their task, the crew returned to England for additional tows, completing 4 round trips over 10 days. Exhaustion and reliance on little more than tea and sheer resolve did not diminish their awareness of the mission's importance. The reunion concluded with a visit to the former site of Mulberry B. Walking along the sands that had once hosted a bustling temporary port, the now elderly participants observed the remnants of the artificial harbour known as Port Winston. Many engineers reflected emotionally on comrades lost during the war and on the enormity of the project they had helped accomplish. One participant summarized the collective sentiment. They arrived in France decades earlier as young engineers, assigned a seemingly impossible task constructing functional harbors where none existed. They were responsible for creating storm-resistant structures from concrete and steel to support an entire invasion within a matter of days. Fear and doubt accompanied their efforts, particularly the knowledge that failure could imperil the soldiers landing on the beaches. Yet, their work exceeded every expectation. Port Winston functioned as intended, supplies flowed steadily, and the invasion sustained itself. Their efforts were instrumental in securing Allied victory. The Mulberry harbors exemplified how engineering innovation and industrial might could overcome challenges deemed insurmountable. Whereas the German military relied on pre-existing ports and fortified them extensively, the Allies generated new solutions, constructing 2 harbors in England within 8 months, transporting them across the English Channel in 3 days, and assembling them into operational ports in just 2 weeks. This required pioneering engineering techniques, industrial output at the limits of British capacity, and meticulous coordination across numerous agencies and private firms. All of this occurred under enemy fire. The success of these artificial harbors demonstrated the power of flexible problem-solving over rigid adherence to conventional expectations. German High Command had believed that a successful invasion was only possible through capturing existing ports. They fortified the coast from Norway to Spain, confident that the Allies would be constrained by logistical needs. They underestimated the ability to innovate. The Allies, instead of being limited by circumstances, created what was necessary. The artificial harbors of Normandy stand as a testament to human ingenuity, a fusion of technical creativity and industrial scale that defined Allied success in the Second World War. More than combat tactics or individual acts of bravery, it was this capacity to envision and execute the impossible that shaped the course of history. The Germans defended what existed, the Allies built what was required. In doing so, they changed the very rules of warfare and demonstrated that strategic ingenuity could triumph over formidable obstacles.